Marshall, and I'm going to be presenting about my work in the VCU Department of Chemistry, specifically the lab of Dr. Julio Alvarez. He is an analytical chemist working at VCU, and in his lab, I and the two graduate students that I was working with were working on something called single entity electrochemistry. And so I'm going to be running down the basics of electrochemistry and then moving on to the methods of single entity electrochemistry. So first of all, what is electrochemistry? Well, as you may imagine, it is chemistry that has to do with electricity. So electrochemistry is the study of electron transfer reactions. These are when an electron is transferred from one species to another. And when I say species, I don't mean in the biology term species. I mean just a thing. A species can be an atom, it can be a molecule. As we're going to be talking about later, it can even be a droplet. So just anything that we want to talk about. And one very important and very prevalent usage of electrochemistry is in electric cells or batteries. This is all electrochemistry that powers a lot of the things that are going on in here. Well, the computer's plugged in, so maybe not that. So the first thing that I want to talk about with electrochemistry is something called an oxidation number. So the oxidation number is a number given to the different atoms within a compound. You don't really see oxidation numbers within elements that are composed of all the same atom, because in that case all the oxidation numbers would be 0. And these numbers correlate to the electronegativity of the different atoms within the compound. A more electronegative atom will have a lower electronegativity, and that's because it pulls more of the electrons towards it. The oxidation number, the oxidation number, which is lower with the greater electronegativity, I want to make sure that I said that correctly. It is basically the charge that each of the atoms would have if all of the bonds in this compound were ionic. In something like, as you can see here, this is the sulfate polyatomic ion, water as well, you see oxidation numbers. These are not necessarily ionic bonds, however, we still, this is how we look at their differences in electronegativity. And this is important when you're talking about redox reactions. A redox reaction is what I was talking about, an electron transfer reaction. And like it says, transfer between the two different species. And here we have a diagram of a redox reaction. They're composed of two parts, reduction and oxidation. So the first part, reduction, is when one of the species gains an electron. And so normally this is from another species that is reacting with. However, there can be what is called a heterogeneous electron transfer, which is when a species undergoes electron transfer with an electrode. And so in that case, a heterogeneous reduction would mean that the species pulls an electron off of the electrode. And here you can see that you have an oxygen atom, and it is gaining 2 electrons and being reduced. Next we have oxidation, which is when a species loses 1 or more electrons. And in this case, the oxidation number will increase instead of decreasing. You can remember this as any of you who have taken AP chemistry will know oil rig, or I just like to think of it as when something is reduced, its oxidation number is reduced. And a funny thing about oxidation and oxidation numbers is that the name actually comes from oxygen, because one of the most well-known redox reactions involves, for example, iron, like here, and oxygen as in the last slide, where oxygen is very, very good at causing other things to oxidize. And so, in terms of the actual description of these equations, I have an example chemical equation here. This is methane plus oxygen gives you carbon dioxide and water. So this is just the regular balanced chemical equation. Next, I have it here with the oxidation numbers. So you can see in the methane that the carbon has an oxidation number of -4. So it is pulling a lot more of the electrons towards it, and each of the hydrogen has an oxidation number of +1. And if you look at all these compounds, the sum of the oxidation numbers will add up to the net charge of the compound. So in methane, -4 plus 1 times 4